All right. So here's our last example for this lesson. And here we're talking about gravity. And a little more specifically, we're talking about projectile motion, right? Because we know that due to gravity, if we throw an object in the air, what's going to happen is it's going to go up and then it's going to come down, right? And so that motion is parabolic motion, right? And it's called projectile motion. And so, and you know, in physics, you'll deal with this formula as well, and you can get more complex where you talk about the vertical and horizontal components of motion. But right now, we're going to talk about just the vertical component. So, so just the height. So projectile motion use this formula, and this is a specific version of the formula. Like usually, you'll see the formula as h of t equals, and I usually put the t squared first just to put it in standard form, but plus v naught t, and then you'll see plus h naught a lot of times. Okay, and what this is the initial height. Usually when you have that little knot there, you've probably seen this before in science or physics, but that usually means initial value. That just means that like the value at 0. And so usually you call it h naught. And so, and this would be v naught. So h naught is initial height. And if you think about it, this is also c, right? So it's also your y-intercept. Okay. So it's your y-intercept. So this value right here is h naught. Okay. So that's where you throw the height that you throw the ball or the object from, or the height the rocket is launched, or whatever the projectile object is. That's the initial height at which it's projected. Okay. And then v naught is your initial velocity. So that's like your b, right? Or excuse, yeah, that's your initial velocity. Okay. And that's usually going to be given. It's usually given. So you'll plug it in. All right. Now this is the acceleration of gravity. The true formula is -1/2 g t squared. So where g is the acceleration of gravity, and it's negative because gravity pushes down, right? And so if we're talking feet per second, since we're dealing with feet here, g is 32 feet per second squared. Okay. If we ever talk about, which we're not in this example, but if we're talking about meters per second squared, then it's 9.8 meters per second squared, which you may be familiar with that too. Okay. So if we're talking in meters, then what you'll see here is -4.9 t squared, and et cetera, et cetera. Okay. So when we're dealing with feet, you'll see -16 there. When we're dealing with meters, you'll see -4.9 there. All right. So anyway, that's our formula, and that's kind of give you an idea. But so what's cool about knowing what we know now is in terms of projectile motion, we can find the maximum height of an object, right, by finding the vertex and the k value of the vertex. So hk, this is our max height, right? By the way, this is a tricky part with this formula, because we know h to be the h value of the vertex, but it doesn't really have anything to do with this h here. So it's kind of a duplicate that is a little confusing sometimes. And then the other thing we can find is this point, which is where it hits the ground. We can figure out how much time the object was in the air, right? So we can figure out when the ball hits the ground, or when the object hits the ground, when the rocket reaches its target, or whatever the case is. All right. So they give us that formula. Notice they don't have a h naught, right? And that's because we're assuming it's from the ground, right? So if h naught is 0, that means it's on the ground. So you can see here that ignoring Martha's height, right? So we're just basically saying h naught equals 0. Okay. All right. Anyway, so basically that's all that to be said. They're just giving us a formula. We're just going to plug in a value, and then we'll do the same things that we did before. So we have this formula. They tell us initial velocity is v naught, and so forth and so on. Then it says Martha throws a baseball with initial velocity of 60 feet per second, right? So that's our v naught. All right. So now we have everything we need to make our function. So we can say h of t equals, and we'll put v naught in there, 60, right? So I'm putting that in for v naught. And then the t's are just my variable. I'm just going to keep those the way they are. So now I have a quadratic, right? For me, I usually write it the other way around, 16t squared plus 60t, but you can write it either way, okay? All right, but now I can do all the same things we did before with the quadratics we had before, because we have this as a quadratic function, right? So what I'm going to do is I'm going to set it equal to 0, right? Just mentally at least, and then I can just plug this into my calculator, right? Really all I need to do is just plug this into y1, and then I can do second, or I can look at the graph, make sure it crosses. It should look like this, right? It's facing down because a is negative, and so it should look like something like this. The y-intercept is 0, so it's actually coming from here and then going down. And so we just need to find out how long after she releases the ball will it hit the ground. So we're looking for this value here. Where does it reach 0? Okay. So do that on your calculator. Second, trace 2, and then go over to this 0. Go left bound, right bound, and then guess, and see what you get. All right, and you should have gotten, for part A, t equals 3.75, right? And then don't forget your units. So we're talking about how long, and so that's going to be measured in seconds in this case, right? So t equals 3.5 seconds. So that's how long the volcano was in the air. Or excuse me, that's how long the baseball is in the air in this case. All right. So the next question is talking about a volcano. So see if you can set up the equation. So it says a volcanic eruption blasts a boulder upward with an initial velocity of 240 feet per second. How long will it take the boulder to hit the ground if it lands at the same elevation from which it was ejected? So basically what they're saying is when they say at the same elevation, they're basically saying, hey, let h be 0, right? Like wherever you start from, that's where it's going to end up. So they're basically making this the x-axis. Okay. All right. So so go ahead and do that. So set up your equation first. All right. So it should look like this, right? We just put 240 since that was our initial velocity. We put that in for v naught. So it's the same formula, but we just change this value out, right? This value stays the same because we're still dealing with feet. And now we're going to try to find the 0. So go ahead and plug that in your calculator for y1, and then use your functionality to find the 0, right? And remember, there's 2 zeros, but we want the one that is that's over here. Okay. Now you might notice on your calculator that your window is not big enough, right? Because your window probably goes to about right there. And so what you want to do is increase your window so that you get that value on there. So maybe so push window and then change your X max to maybe like 20, maybe double it. Instead of 10, make it 20. And if you need to go higher, you can go higher from there. But I think if you get it to 20, that should fit the both intercepts. And so then do your calculation, and you should get x equals 15, or in this case, t equals 15, sorry. And we're talking about seconds still, right? So it took the boulder 15 seconds to hit the ground after it was erupted from the volcano. All right, so there's an application that we'll see probably again and again. This is a very common application of quadratics. And there's a lot of other applications too, anything that goes up and comes down, but also anything that goes down and comes up too. You know, sometimes like stock prices or business, profit loss, different things are sometimes measured with parabolas as well.